There we go.
Hello. How are you,
Hi
Ethan?
there. No, it's nice to meet you.
Good to meet you. Where are you calling from?
We're out of Austin, Texas.
Oh, nice.
Yeah, no, we met Tim in person out at one of Josh Bayer's event, kind of Capital Factory side years back, but he had an interest in what we were doing, and eventually, glad we could start to kind of reconnect. So he said, whenever there's a venture appeal to it, let's talk, and now we're talking. So
Excellent.
Excellent. Nice to meet you, Ethan.
nice to meet everyone else that just joined too. Perfect.
I like your shark painting.
Oh, thank you. Local artists. I have a couple of his works on the side. He makes some kind of nice perspective drawings and things like that. So, always appreciate his stuff and try to support whenever I find him.
Yeah, I like it. And is that an award or a tchotchke on the
Yeah, no, we have a couple awards. So, we've won different manufacturing awards in the past too. So, kind of keep them remind me that we're doing something good here on the backside.
Excellent. Very cool.
Thank you.
Hi, Ethan.
Hi, Tim. Good
How
to
are
see you. It's
you?
been a couple of years, but appreciate the response to the emails and glad to reconnect.
Good. Yeah. So tell me what's this business called? 3D tech, creative
Yeah,
3D?
so Creative 3D Technologies. We're on the kind of think industrial machinery for a whole lot of different industries. We're producing them out here in Austin, Texas. We have a facility that we're making them right now.
What do you make?
Yeah, absolutely. I can jump straight into it. I've got a couple of slides that I prepped kind of specifically for this, just to give some visuals, if that would help. Give me just a second. Perfect. So we make something that's an entirely new classification of machinery. So, we make a tech that's called single cell manufacturing. Basically, the goal is think factory in a box. So kind of what 3D printing wishes it would have been instead of just a way to make parts. We're essentially one system that can move in all the right directions, take the right chemical inputs, has the sufficient speed, torque, everything else you need to do the jobs of a lot of different, very separate production methods. And instead, we've put it all into one box. So we're doing anything from making self-healing drones end to end on one machine for the DoD to, and we're doing a demo, I think next year, where we're putting just raw inputs and making a full laptop assembled, wired, and produced off of a single system. We're trying to essentially be an option to China in terms of where and how manufacturing is done. But think the most kind of relevant side is probably the semiconductor fabrication that we're pushing at, which has sparked a lot of conversations and one to definitely think curate a lot of this towards that. But happy to get into that whole section too.
Okay, so I mean, your 3D machines are gonna do metallic and plastic and
Yeah.
silicon, but and then you end up with a chip. Um, I mean, are you thinking you're gonna go to what are they at 3 nanometer widths? Or I mean, are you thinking, hey,
So
this is going to compete with TSMC, or are you thinking this is going to be a nice, we can put together a quick chip that looks like an 8086,
yeah, so we would be more competing with ASML themselves. So actually, there is no 3 nanometer chips on the market right now. It's a bit of marketing BS right
Mhm.
now, and I can kind of goes into the problems. Everyone right now is actually stuck at 8 nanometer right now, whether you like it or not. If you read, TSMC saying, "Hey, we're using a 3 nanometer node to produce Apple's next gen chips," the line width isn't actually 3 nanometers. ASML is stuck at 8 because what they do is they take a 13.5 nanometer light, they bounce it across a bunch of mirrors, project it through like a mold, a mask, and they make a chip. But it lays on a 13.5 nanometer light and patterns it down to 8. 8 nanometers where everyone's stuck at right now without exception. The problem is because everyone's been stuck at 8, they've marketed it otherwise. So if they make a new node, if TSMC makes a new node and they double performance, they double the speed, instead of marketing as 8 because they double the speed, they now mark it as a 4 nanometer node, for example.
Mm.
So that number used to
I
align with
see.
the
Okay,
actual
so
chip line
so
width.
can your device make an 8 nanometer chip?
We can do below 2, actually. So we are actually capable of making the leading edge of chip fab. And happy to kind of go into things because
But
what we're doing.
wait a second, chips are made in such a complex way.
Mhm.
They've got they've got the etching and the bath and the
Yes,
the acid, the sun, the print, the um, photolithography. So
correct.
many things go into a chip. Are you doing all of that in one device?
We already have, actually. We're doing end-to-end fabrication. We're actually going to demo it during South by Southwest this year and an on-site event in our facility. But we're producing the wafers, we're post-processing them, we're packaging and cutting the packaging, and then that same system can switch pallets and, pick and place and wire that into a drone if someone so desired, for example. That's what I meant, we're doing end-to-end fabrication, but in the semiconductor side, think of it like a fab in a box. We're your ASML, we're your Tokyo Electron, we're your NXP, and we're like a self-contained clean room and doing that end-to-end production in one box. Because right now we see there's a lot of issues in the market. I mean, if we look at things like, well, kind of right now, for example, like data centers are over demanded. If we're looking at the increase in how AI has been growing at a trajectory like this, and the data centers are over demanded, they're demanding more processing power and they can't keep up. And the silicon that's running them is bottlenecked for that, for mining and a lot of other things. And because
So,
everyone's
is your specialty going to be um, making a ton of, I mean, the way semiconductors are made is a wafer chip, they
Mhm.
divide it up, they put it into a chip.
Yep,
You're going to make a chip at a time, right?
not quite. So we're still creating full wafers of chips. Actually, I
Okay.
can, I had a kind of a general structure, but I can
So
go into.
are you going to make a wafer that is, so is your like the customer that's going to want you, are they the ones who are going to do a million ASICs, or is it going to be the one who says, I just need, 3 wafers?
It's a variety. So I think we hit three main markets in terms of semiconductor fab. The first one is that we are a massless mode of production. Right now, if you want to design a chip, you have to do $1 billion tape out per design. So you design the chip, you simulate for millions of dollars in NVIDIA, you go back and forth until you feel it's good to go. Then you pay for them to make the mass, the equivalent of a mold, and you do that tape out procedure, set up production. We're essentially 3D printing the chip. So we found a new light source. We invented a new type of compound mirrors that better distills the light. We use less mirrors in the ASML, which means we're projecting light through a shorter distance, which means we can better focus that light down to that swept water window 2 nanometer wavelength. But the point is, it's kind of like 3D printing where you'll project an image and it'll lay down a layer of plastic, keep projecting an image overlapping to make a product. We're doing that with chip fab. So you don't need that $1 billion tape out per the chips, which enables a lot of innovation. So we're even having conversation with AMD, for example, who doesn't make their own chips. They offshore them to TSMC. But if they can save the millions of dollars that they're simulating with NVIDIA by getting a unit, producing the chip, and then physically plugging and testing it in-house, and then on the same unit going into production on it, there's some options there. So there's the R&D and the prototyping. I think there's also the specialty market. It's labeled more than more in the semiconductor space, where if you have advanced medical chips, if you have a lot of things that doesn't make sense to do the $1 billion tape out, this system doesn't need, you can have, one wafer chips be different than the other. Without fail.
Have you made a chip yet? I mean, is the machine
Yes.
working?
Yeah, we have. We've done so. We've prototyped it. That's what I mentioned. We're doing an actual public debut of it this year. And then the final method is actually that our method of manufacturing is a lot less expensive than what's currently out there. So I can explain it, but we have 2 different systems, and those are the systems that we currently sell that kind of operate as like that factory in a box. We've modularized it. So if you want to go from 3D printing to milling to lasering, you pull off a module, you slap on the other one in seconds, and you jump from production type to production type. These systems, basically, we've modularized the production. So if you want to produce a chip, there's 2 modules you buy. One does lithography, one does ink jetting and replaces the trays as well. But long story short, you swap those out, you buy the module from us, and now your system can produce chips. With that, there's one that we have at leading edge, so it can do 6 wafers an hour exposed, and it can do all the post-processing, but it costs us about $310,000 in cost of goods sold to produce the module for it. but we actually sell it for 2.5 million, which, that outperforms the cost of the machine. But the bottom line is, if you look at a 100+ acre multi-billion-dollar fab, they're doing 170 wafers full of chips an hour. They've built themselves to be a clean room. They're massive operations. We're nowhere near 170 wafers an hour, but we're also nowhere near the 100+ acre multi-billion-dollar cost. If someone bought about $60 million of our units, which we already have interest for, we have people saying, we'll buy out your first full 3 years of production worth of these things. But if someone buys out the equivalent amount of units, they can easily meet or exceed that 170 wafer an hour number, not need to build a warehouse to be a clean room size, not need to be so vibration isolated. They can use less chemically pure photoresist materials, which means you can make cheaper chips, and exponentially so, and bring it to market with new designs a lot quicker than a competing player.
Are you gonna sell the device, or are you gonna sell the service?
Sure. So we have a couple modes of revenue. What we do is, like I mentioned, we're kind of doing all-in-one production, and actually we have units that are doing production in a lot of different areas. Semiconductor is just the newest market we're moving into. So our model is we sell the unit itself. We have pretty high margins on the systems, but then people buy those systems and they buy the modules depending what they want to produce. So if you want to make a chip versus packaging versus assembling, wiring, whatever, you buy different, we call them tool heads. You buy the different tool heads and you buy them in the machine. They can be cheap, or they can sometimes outperform the cost of the system. So they buy the unit, they buy modules that expand. They also buy modules to keep relevant. For example, because these systems are doing standard 3D printing as well. Industry kind of leading for precision printings, 85 micron. Our machines are doing 60, but they're built to go sub-micron. So if we're just talking standard 3D printing, for example, the machine's better than the tech right now. So 5 years from now, when it's more competitive, someone can buy the latest module, slap it on. In addition to that, there's software, there's material, there's care and service, there's the whole ecosystem that comes with it. So a lot of different revenue modes for the systems that we sell.
So is the idea you'll sell the system, and then you'll sell like the metals that go into it, the plastics that go into it. You'll
Correct.
sell upgrades, you'll sell all that stuff. But,
Upgrades, consumables,
but
service,
you're not
care,
going to sell
software.
wafers. You're not going to like say, okay, we'll make you a wafer.
Our goal is to be the ASML versus the TSMC. So we would sell to the TSMC, or we have other folks that would be building fabs and already are offering and giving us proposals to build fabs around our systems, for example. And given that ASML owns over 90% of the 100 billion plus system market, and they're pulling over $30 billion a year in revenue, there is no competing leading edge fab right now. And the only way to beat them is either A, you undercut their production costs, which is hard because they have sheer output quantity numbers, or B, which we've seen build entire countries, is if you get to the next gen fab first. For example, like Japan and Nikon used to be major players in the semiconductor space when it was still imprint lithography, like stamping almost. And then they didn't jump to the latest techs and look at how that market share went to China and Taiwan. The market's always grown in spikes and plateaus. We're at a plateau right now where everyone's stuck at 8 nanometer. We believe we have tech that can be the next spike that enables people in terms of where, how they produce these things, and enables them to actually innovate and iterate, which, like I said, there's been a cost barrier to actually doing so in the past.
How far along are you? Have you raised money?
So a bit. So in terms of where we're at right now, I'm just kind of jumping through different slides, but basically we have a bit of a plan that we're using to attack market. So like I said, the semiconductors fab is one facet of our box. Basically, our goal is to put as many types of production as we can into one system. So already the system are doing things like milling, lasering, pick and place, 3D printing, and metals, carbon fibers, ceramics, silicons, things like that. And we're essentially trying to release and enter now the semiconductors with the new modules. So in terms of kind of phases of where we've been at the company, we unofficially started this journey in 2015. We legally in 2017 formed the company. And it's been a long R&D journey since. And these machines, it took our lead researcher 20 years of his life to design the software, even design certain parts, because a lot of the designs that make these machines function, you cannot design on a CAD or a 3D modeling software. So it took him his life's work to make the software even do it. And can't design it, you can't produce it. It took us 5+ years to actually make the systems, even make the machine, and 200 iterations to get it right. But what we did was we started in market. Initially, our kind of beachhead is the 3D printing market, because despite pandemic, recession, supply chain crisis, it hasn't seen the falters that 96% of businesses have. It's at a CAGR that's more than double the current rate of semiconductor fab, actually. And in addition to that, there's no dedicated leader. It's still a wild west. The people that dominated the industry 2 years ago versus 4 and today are all different. So what we first did is saying, hey, test it out. Is there even a market for a machine that can do more than one function? Because everyone is used to one machine does one specific task and one specific material for one price point of customer. So we released a unit. First debut, we sold out the entire stock of in the first 2 weeks of announcement. We later made a more evolved version of that unit, kind of pushing towards that all-in-one production idea, which is what we sell currently. And currently we're in phase 3 of kind of this chart where we're allowing, starting to release different modules that go from 1 industry to 2 to 3 to 4. Think of it kind of like an Amazon play. Instead of being a retailer of everything out the gate, doing 5 different markets, they started in 1, blitzed it, and then leveraged the tech to go from 1 to 2. That's what we're doing with a current product to lead into more advanced systems that we developed prior.
So right now you're selling it sort of as a research tool, and over time you'll eventually make it so that it can do semiconductor chips. Or are you saying we can do them right now?
We have the ability to do them right now. We're at TRL 5 essentially on an Army TRL where we've actually done it, we've proven it. Now it's going to kind of public debuts and higher phase of testing. For example, we have the CTO of Intel coming in the next few weeks. We have some very strategic folks involved on the venture, since we have the former CIO of Citadel involved, helping us on securities and a lot of other sectors, great making connections, have a very prominent, strong team behind it. But what we're trying to do is get people even used to one machine doing more than one task. All machinery is colluded. I speak at the UN on this exact same topic. One machine does one function for one customer, and that hasn't changed in the past 3 to 5 decades. That's why we have the modern day production line. The more advanced the product you want, the more machines we add to the line, the higher that product cost goes. So you have to comp the cost of the machine. We've made it all.
Does your machine do it all simultaneously, or does it do one function at a time?
Simultaneously. So we're able to use multiple processes at the same time in a part. So for example, we made a self-healing drone for a DoD prime contractor. We told them, give us a task you think you can't make for the next 10 years. We'll do it today. So we printed the carbon fiber, we milled it, we picked up and dropped in the motors, we fabbed the chips, post-processed them, picked them up, wired them, and built the whole thing around it. We made some of the first 3-dimensional circuit boards that are going vertical and diagonal. So made like these 2 foot by 2 foot drones in less than 30 hours, 4 them at a time. And we did so at a cost that if China could produce it today, we would have been 20% less in their mass production.
So the carbon fiber, how's that work? A drone has metals and plastics. It also has carbon fiber.
Correct.
Carbon fiber does not that I know of, extrude.
Correct.
It's laid on with like a glue or whatever. It's kind of molded.
Yeah, so that's a little bit of the perception problem that we're trying to overcome, because everyone thinks, again, one machine does one production type. What we're easing people into is, hey, if you take this box, you open it up, this is what I call the tool head. You pull off the tool head and it can swap into different types of production. But those tool heads don't necessarily just need to be, for example, 3D printing or milling. These are just encompassing whatever production tool you need. So if it's trying to do laser cutting, instead of having a full laser cutter, we distill it down to just a laser. If you want to do milling, instead of having the whole mill, and we just distill it down to the spindle. If you want pick and place, just the thing that's going to pick up and drop. Same with semiconductor production, just the lithography and the ink jetting. And so essentially modularized production and built a very high performing system that can actually support that tech.
So, okay, so you can pick and place the wings or the whatever. So, how much do you sell it for, and how much does it cost you to make? Oh, here it is, 150.
Yeah, so 2 different systems. The one that we have in market right now is Evo. It's kind of that transitional product. The base retails for $25,000. At scale, costs us about $6,000 to produce. But again, different modules for it have different cost points. Not everyone needs semiconductor fab. So Evo is initially going to do lagging edge fab. All the things you buy from like a Murata, for example, things that populate the rest of the board. That module costs more than the machine because not everyone needs semiconductor fab. So we sell that for $120,000, costs us about $12,000 to produce. Dyad, our more advanced system, much larger, moving at a faster pace with higher precision, etc. We're trying to ease people into Dyad through Evo, because Dyad's doing 20+ manufacturing methods in one box, and we think it's a little bit of a headache for people at the moment. So that one's doing the leading edge fab. So we're estimating a 2027 release for that. And the module for that, costs 2.5 million, cost of 310,000 in COGS to make. While the system itself, we sell for 150,000 with 20,000 COGS.
Wait, what's the fab module retail? What does that mean?
That's
You
for chip
buy-
production. So if you want to take this box and turn it into, from like a factory in a box, turn it into a fab in a box, you buy the module from us. Like those things I showed the swapping of in the
Oh,
video
I
just
see.
now,
So the
you buy those from
module,
us.
the modules, so you can buy a regular, 3D printer for 150K, but if you want the thing to move different heads in and out and all that stuff, it's 2.5 million.
Correct. Yeah, it depends. It depends what you're trying to make. So, for example, like our bread and butter and our secret sauce is the machine itself. Having a machine that can be this large, maintain that precision, move at these speeds, rigidity, and everything else has been deemed impossible for decades. We are the first to make it. And, if we want to do printing versus milling versus lasering versus any other different type of production, the machine has the spec to actually support that. That's been the main divide. And usually if you're trying to like cut high tier metal, you make a high torque machine built around a tool. Instead, we built the most capable machine we can and made it agnostic to what tools it uses. In terms of where it's at, those units are deployed right now. We have those Evo systems in market. So we're in the hands of Disney, US Army, and their advanced autonomous vehicles labs, automotive manufacturers, medical device companies.
When are we going to see actually a finished semiconductor come out of your machine?
We've done it already. Like I said, likely this March we're doing a public debut of it. I've got other examples.
And
I
it's
can even
it's a working semiconductor?
correct.
It's a
Oh,
full chip or a wafer?
We did so produced the wafer first, post-processed, packaged, cut, made an end chip from it. So it was the full suite kind of breakdown cutting, but we have, because I have a data room here that I can pull up an example of.
So you did the lithography on it, all that other stuff too?
Yeah, and we've even done it with non-so-traditional components like electronics boards too. So this board's about 0.15 millimeters in diameter from end to end. So small and something that's a less traditional use case. And we're able to use and produce PCBs even with the same method. And so happy to send, we have a little 2-pager summary on it that I can send, directly after this too, if it's of interest.
And what's the physical size of it? It looks like it's about 2 feet by 2 feet by 2 feet.
So this one's, so the unit itself?
Yeah.
So the units themselves, to give some perspective, I'll go back to the photo that had the units. Dyad, this system, each of these squares here is about 5 foot by 5 foot. So it's a larger, more industrial one. While the Evo system right there, I can pull up another example. So in the 30 under 30 article we had, they have me sitting in a unit itself. So internal is about 3 foot by 2 foot by 3 foot in that volume. So compare that to me as someone that's 6'2" sitting inside of it.
So how much money have you raised to date?
Yeah, so we've not too much. So we've got one of the larger IT infrastructure companies in the world on a kind of our founding date, because they said the second you do something venture backable, we want in. I know the kind of business you run. So Creative ITC, they're out of the UK. They're one of the larger players in the EU. They invested us day one and shared their team with us, which was helpful when we didn't have one. And then we did a pre-seed, which is about 830,000. So we had we brought in some early customers and folks that were interested in the technology, saying if you want to get it faster, best ways to fund us, along with Alumni Ventures, DieTech Ventures, and a couple angels. And then now we're currently in a round that we're at the very tail end of as well.
What's
helping
that
scale.
round?
So we're doing a $5 million round. It's being matched by non-dilutive parties. So we're gonna have about 15 million to walk out with. We have 4 million of that 5 right now. We got in some strategic early investors like the Shaw family out of New York. They were early into Google. Stella Capital was early into SpaceX. Linus Ventures did DocuSign. So we have some notable folks involved on that front, along with return investors from our previous round.
So $5 million round, what's the valuation?
We're doing it on a safe note. So it's a $20 million pre-money cap, 20% discount rate. That's currently what we've been doing. funds are being matched. So for example, if we build our 2026 facility in Cedar Park, Texas, they're close to Austin, Texas, but a little smaller, a little more hands-on. They said, we'll be your local partner. We want to help you out. They're co-signing grants and things with us. And so they're matching the funds, actually a contingent that we move there 2026 and build our next facility out there, along with, we have the Texas Semiconductor Innovation Fund that we're in the running for. So it's a $700 million allocation. We have support of, the chairman of Tokyo Electron, Opportunity Austin, a couple local players. Likely we're getting, 10 million, but, under promise or deliver, we're at least getting 5 from that, which following the round gives us within 6 months of close, 15 million to work with on the low end.
So of the 5 million, how much is spoken for?
4 million so far.
Okay.
I said tail end of the round. There was a little less, I think, when we initially contacted. I think we're at 2.9 then, but it certainly moved. The goal of that is increased production. Right now, we're over demanded on the Evo systems, even without any of the add-on modules for it. And we need to scale. And we have a couple examples. I'd be happy to pull one up, assuming this stays more private. But so this is an example. This is from Worth. They're one of the larger privately held manufacturing parties in the world. They got one of our Evo systems tested in their facility in Greenwood, Indiana, and beat the hell out of it. They enjoyed it. They realized it could actually produce a qualified product. That's been one of the biggest issues in deploying manufacturing to any front line, where the manufacturing tools never told you this has the right weight, the accuracy, the tolerance spec, anything else. Our machine can actually do that because it generates a lot of data. And so they said, hey, that data can actually be used to tell us that if we use this thing in Greenwood, Indiana, that if we put one in Germany, it can make the exact same part to the exact same spec. And between there's a company called Migo Water. They do this shipping container size water filtration that can turn anything from fracking water into drinkable. Following my UN speeches, the African Union and the US Air Force have all order interests above the 50 million mark, and we can do a couple units a month production because production
How
has to be
much?
in-house.
I mean, some of those things are very different from
Yes.
semiconductors. What do you have to do in each case? You create a new print head kind of thing?
Exactly. So different types of production are different print heads. And for each of those customers, right now, the Evo system and what it can do is capable enough for, the Air Force. They have the C-5 Galaxy, largest aircraft in their fleet. It's no longer production. They're running out of parts. So they like the metal parts it can produce. I made half the parts around my car that I drive every day and drift around. So
How about your team? What's the team look like?
yeah, absolutely. So
And
we've got
what's your
folks.
background?
Sure.
Okay.
So my background's been the 3D printing industry. The second the patents dropped, I was in it. I ran one of the first refurbishing companies in it. So buy the machines broken when no one else would, fix them up, and we'd make new parts for them in-house and add new functions and features to it. And we sold anyone from hobbyists in the garages making RC car parts all the way up to parties of world militaries like the Argentinian military. They supplied a lot of our systems in their bases. Eventually, manufacturers came to us saying, hey, well, why aren't these machines failing? And from this no-name refurb, it's because of this development. Hey, can we license that from you? We accidentally turned into a bit of an R&D arm. So we put some significant IPs and a lot of companies on the map through our work and leverage that lucrative business and the finances from it to fund this company and exit that. So I've been in the industry for a while. I'm a United Nations subject matter expert. I speak at their conference of parties, their general assemblies and things like that, and sustainable future manufacturing. And thankfully, because I've been in the industry for so long, we have a lot of heavy hitting folks. Like Matthew Hines is brilliant. He's leading a lot of semiconductor initiative, very technical, but he is expert in the industry, been there before. He's made technology and software suites at high tier Ivy League university researchers said it could be impossible and proven them wrong. In addition to that, Chris Lombardi, for example, I want to keep the technical talent as the main 3 names that we show, but we do have a team of about 17. He's MBA. He's made some of the most prolific firmware platforms in the entirety of the manufacturing industry. And their involvement has been, I think, critical on the technical side. So
he's an internet ghost? What's that?
He's not one that wants or can be looked up. He has done major things in striving and pushing the industry forward in the 3D printing industry, but he is not one that wants to be a public figure. But he is the inventor of prolific firmware software or firmware platforms like Clipper, for example. And I am privileged enough that usually when you have a startup,
Where did he work before he joined you? Where was he?
He's had multiple businesses. He's mostly kind of run his own, but he's always been producing things like that firmware platform on the background for himself.
So
And more than anything, publicly pushing
he's
it.
more of a consultant then?
No, they both work full time for us. What we've done is we've kind of divided the CTO role a little bit, where both of them are brilliant leaders. Both of them can make an end product, but they'll take very different ways to do so. So Matthew Hines leads research, basically bringing a concept from concept to working product. Then it goes into Chris' side, which is all the development side, where he takes that working product and makes it into something that we can deliver to a customer. And so we separate them, but they're both brilliant and have a good track record in the industry. And as noted, we have a team of about 17, so we have a lot of production hands because we are physically producing these machines in-house already. We're selling, shipping them, and making them in-house. Along with that, we have some pretty notable advisors, like I mentioned, previous CEO, Citadel, directors of Plug and Play's advanced manufacturing side, and folks that I can say confidently are better than I am in their own fields.
Questions from James, Max, Andy, Megan?
Do you have a piece of paper or pen to write down? I have a list of questions and you can answer and based on.
Yeah, absolutely. Let me
So-
move this over here and get some notes out.
Okay, so additive manufacturing is well known in semiconductor fabrication. So I think this makes sense. But historically, it's been applied to mechanical devices because people didn't know how to do diffusion. So
Yep.
maybe you can help us explain to us how you make diffusion. So that one device you made, is that a logic device or is that a mechanical device? And specifically, how many transistors or how many, I guess, sub-devices are there on that chip?
Sure.
And I also want to find out your customer pipeline. I think you threw up some revenue numbers, just kind of educate us on the customer pipeline. Specifically, maybe you could address what I call the speed and the volume conundrum. Whenever you have a very fast chip, oftentimes this equates to some sort of consumer device that would have billions of units, ultra high volume manufacturing. And those are, I think, most suitable for these large fab lines. When you have more of an exotic chip, like analog, whatnot, you have smaller batches. I
Yep.
think the only exception I could think of is probably the military. That's why I noticed you list Army. So I'd like to just
Yep.
know your pipeline and how you think about that conundrum, right? If you have this sort of, you reach 2 nanometer, but 2 nanometer, I think the people who want to pay for it are the Apple, Samsung of the world that want to put in
Yep.
billion phones to amortize over the cost. But then that is not what you're building here. Right? This is not at least I think of the ultra high volume.
Sure.
And then switching gear to the financing, who's the lead and how much is the lead putting in when they set the price of 20 million cap? So
Sure.
that's a list I have. I don't know if my colleagues want to add to that list and you can just kind of answer
Yeah.
them.
No, happy to take more and add to it. No worries. If not, happy to kind of go on to these ones too, if there's no other questions at the moment.
Oh.
Sure. Okay. Yeah. So I think it'll be helpful for me to kind of describe how we're doing some of the chip fab a bit to just kind of make it more direct. Basically, we're not doing anything that's exponentially new. I mean, the light sources that we have been tried and true and used in different industries for a long time. They're just more condensed than a ASML fab. So we're taking things like soft biology X-ray microscopes and projecting light through them in reverse to do essentially DLP 3D printing of chips. So trying to get more technical with it. Basically, we're taking the light we've made.
How do you do diffusion? How do you make the PN junctions? Because that involves, like sourcing of dopants going into the chip. So maybe you could educate me. How do you even make a transistor? Are you making transistors?
Yes. Admittedly, some of the things in this technical dive are probably going to be out of my expertise. Like I said, not afraid to admit when I don't know something. I am the conjunction of both the business side and some of the technical. I'm pretty technical myself, but I would be more than happy if I can't answer it properly, to bring in the expert that's actually leading all this, who can definitely give the technical background that I might not be able to. But
Who's the inventor of the technology?
Matthew Hines on our team that I mentioned is the one spearheading this at the moment.
Okay. And then he had worked at semiconductor companies before, sounds like.
Yes, he's done semiconductor fab and been involved with a lot of different semiconductor
Which
projects
ones?
in the past. That's one I'm gonna have to ask him as well too. But
Okay, okay.
I'm
So
happy to
find
write
out.
down a list of things to
So
bring back to Matthew.
the reason why I ask is making, if I fast forward the clock 10 years later, you become a very large decacorn, replacing ASML. By the way, ASML is only a point tool. They only make the lithography stepper.
Yep.
So you have, apply, you have.
Yeah, I do the EUVL.
RAM,
Applied does the
resistors.
materials, the photoresist go in. Yep.
Right, so to make billions of these chips is actually very difficult. And I'm just very
Yes.
curious which companies he worked at actually had already produced these units, because having some manufacturing experience would help. I mean, you don't have to have it, but I think having some as part of the 3 people would help you. But
Yeah, and I
it's
can
not
say
a
we do have some folks that are kind of tenured veterans in the industry. I mean,
Yeah,
folks
good.
are taking current positions in the round, and we have, the person that did diligence on us for Cisco is taking a personal position in it. We
Wow,
have former
great.
executives like Peter Hahn that are in the industry that have been in there. And like I said, recently we brought on the previous CIO of Citadel Securities, Noah Batar, who has been a massive value to us. He wants to be as stringent and kind of break down and really make sure everything on this works as it should before we really start talking about it with us.
Yeah.
And that's why he's able to pull in folks like the current CTO of Intel to come out, qualify, and work with us on this as the value that he adds to his advisory position.
Wow,
But
that's very impressive. Okay, so I'm sorry to interrupt. I'll let you go through that list.
no worries. But happy to kind of give some example on the semiconductor side. We do have a larger white paper that Matthew wrote that dives into all of it. But long story short, actually, I'm going to pull up one more document just to kind of show here. But long story short, the way that we're able to really, from my understanding, I'll give you the limit of kind of my understanding is that, think almost DLP printing of chips. We're taking a different light source like extreme soft X-ray biology microscopes, taking that, which is able to do that 13.5 nanometer light, but we're using different types of mirrors, actually making our own types of compound mirrors and using a fewer quantity of mirrors that we can actually use to better direct that light. And then, pushing that down to a swept water window wavelength to actually produce different chips. So we have moving platforms and things that are actually having project and work on some of these systems. But any more technical than that, I'm happy to pull them in.
Yeah, is it possible you actually have to send your chip out for diffusion, etching, and come back and for more lithography?
So for different post-processing, yes, we kind of swap the platforms to be able to do that. That's one of the benefits of actually being able to swap heads.
Okay, so I think you are absolutely correct. You will replace ASML, but I'm not sure if you replace the whole fab.
Not quite.
Yeah.
In terms of the same efficiency, yes and no. I mean, there's different instances. That's why I kind of label the 3 markets.
Yeah.
I think, like I said, that more in the specialty and the prototyping are major ones that are just not being served at all right now.
Yeah.
In terms of other types of production, yes, we're doing the lithography and actually producing the chips, but this same method is essentially exotic material, fine precision 3D printing. If we wanted to, I'm using photoresist and other materials. If we wanted to enable someone that already has ASML for systems, for example, we can produce mass using the same method and mitigate tape out costs if someone want to. And that way we see it as a true blue ocean and not as necessarily a direct apples competitor in that sense. But in addition to that, the same system can do the post-processing and washing and things like that in the same environment and just kind of swaps trays to do so. Or if you really want to up the efficiency, instead of buying the whole semiconductor fab module over again, buy a second unit, put them face to face, have one do processing, cutting, packaging, while one does wafer production, have them move back to back, then off on the line once they're fully produced. That's one of the things we're looking at for someone to do higher output, which kind of, I guess, follows into the speed versus volume conundrum. One of the things that we're doing, because like I said, this isn't the highest output now. It's about 6 exposed wafers an hour if we're just doing the fab portion alone, not to mention the post-processing. But if we're comparing that to a
Sorry
300,
about the speed. The speed is clock speed. So
sure.
it's
So that
the
depends
clock
more on the
is-
photoresist side. You can use less chemically pure photoresist. So we can, if you want to use a less pure photoresist, we are doing defect correction because we have multiple projected images that are overlapping. We can detect nanoparticles, things like that. If you want to make your first runs on a less chemically pure photoresist before using the expensive stuff, you can, which plays in that prototyping market or the less refined market. But that quality software and everything else we have is pretty critical to making final end use product chips. Outside of that, yes, we're getting competitive. I mean, sorry, a lot of thoughts in the head. You can achieve the clock speed. So it's just dependent on the photoresist. And again, we're not a materials company. So we're still working with folks like Applied that are making these photoresists. And if you buy the nice chemically pure stuff, you can get there. We're able to do that same defect correction at the leading edge to be able to make pure chips for that.
I guess my question is, if somebody makes 1 billion chips a year at,
Sure.
15 gigahertz at 2 nanometer, gate length, they have high volume manufacturing. You could actually do it for them, but they wouldn't use this type of machines because they need high volume machines that can crank out lots of chips at a low cost.
Yes. So
Right? So
I kind of want to
that's
first.
the conundrum, right? You could get to 2 nanometers, but then they need 1 billion chips. And I
Correct.
think to make 1 billion chips cheaply, it's a different type of machine. It's a parallel processing machine versus 3D printing each one. You see what I mean?
Kind of. So that's the differentiation between SLA versus DLP. So usually if we're talking 3D printing, like fine detail, you look at like a Formlabs, for example, it's one laser and it kind of etches out the thing. That's not the type of process we're doing. DLP 3D printing, which is kind of what I'm referencing, is basically you project out a whole image. So in our case, we're basically projecting out all the different chip architecture at that swept water window wavelength. We project that out and it makes the whole layer of chips at once. We project the next layer and we keep overlapping those projections to make the layer. So it's not like a laser, it's etching, it's the whole image, which lets us do output production. But again, we're not the output of an ASML, and the ASMLs are where you have your really high output systems a lot of times. We're 100 times less output, but we're 1,000 times cheaper. We are disproportionately cheaper than we are output. So it is more sensible, especially because you take out the tooling costs to actually scale with us. That's when I was giving the analogy. If we're talking about 100+ acre multi-billion-dollar fab doing 170 wafers an hour, we're at 6 wafers an hour. But if you buy sufficient quantities of machines, it's going to run you less money to have and meet that same quantity output by buying more machines than it is for you to buy those same systems. And we're always looking for different methods to actually increase output. This is something Matthew can definitely talk a lot more on. But we're taking, for example, one of the newest developments we have is we're taking nano imprint lithography, the stamping method, where they would mass stamp and produce the chips, basically leveraging our method to create new leading edge and taking that to the leading edge to actually do the higher tier semiconductor tech, and kind of cranking out things with new imprint lithography. And
Okay,
so
maybe
that's
you can
another
just
method we
address
can increase output.
Address the pipeline and then the lead investor.
Sure. So that's what I was trying to clarify of kind of products that are out there and where we're at. Our whole bread and butter is not just the semiconductor side, though we think it's a very lucrative development. Our goal is true factory in a box. So making the semiconductors is one part of it, but making a fully finished product around it is major. That's why, we were talking about one of the debut models we want to do for this system is literally producing a laptop end to end, because we played around and dabbled in battery production. We played around with fans and all the things that go into it, through the plastics, the metals, the wiring, the assembly. We have systems already doing a lot of that, and that's kind of one of the big debuts we want to show. Our goal is factory in a box, not just fab in a box. And so that's the differentiation I want to first convey, because what we did is, I'm going to pull up actually a bit of a different presentation, because this one I try to just curate to be semiconductor focused.
I don't want it to derail your train of thoughts.
Sure.
I just want to know who are the customers who place order, what did they order, so we get a
Yeah.
education.
So to give some clarity,
yeah.
Our like I said, total goal is to make factory in a box. We have this system introducing people to that concept. People are used to one machine doing a dedicated function. No one's really ready for a machine even doing 5 functions, much less 20 like Dyad does. So we need to ease people into that. So initially, we do have this system, we call it Evo. We're initially targeting the 3D printing market before the semiconductor market. So right now, we advertise Evo saying, if you want an $8 million suite of 3D printing tech, this is your machine that does it all. So if you want tungsten, titanium, and Inconel jobs of a $3.8 million system, we do it. You want your $2 million aluminums, your $1.2 million steels, ceramics, large, small, plastics, whatever. This is your all-in-one. And then we're slowly introducing these modules, these tool heads, which consist of semiconductor production as well as a tool head. There's an add-on kit. We're slowly releasing those to get people used to the concept of one machine doing more than one function. And that's how we go from 1 to 2, 3 to 4 industries instead of being unfocused and attacking 5 at once. So the initial thing that we're selling today, right now, as we're releasing more of these tools this year, is that $8 million suite of praying tech in one box. And so basically a lot of people who currently use 3D praying tech or otherwise are using it. So that's why we have Army clients using it for parts they can't normally produce because they have advanced topologies. We have a lot of people that want to use this as a risk mitigator for supply chain because we can make an end qualified, ready to go part. And to the confidence level that I trust my life behind it every day in my car. But in addition to that, we have prototyping, we have R&D, and we have plenty of even startups that buy this thing, finance it, go from concept through all the iterations, and then into several thousand a unit a month production off the same machine actually getting in the customer's hands. So we have a pretty large variety of industries that purchase that since we can handle plastics, medical grade materials, orthopedic, metals,
Got it.
ceramics, etc.
Thank
And
you.
so that hopefully explains, I think, a little better the current customers that
Yeah.
are buying these systems. But
Okay.
we do have a lot of interest already papered down for the semiconductor tech. Our thing is we've not publicly debuted it yet. We have a little more R&D we want to do on it, which is why there's a venture appeal still.
Yeah. Great.
But given that we haven't publicly debuted it, we're still getting interest. And we still somehow ended up with conversations with NXP, Tokyo Electron, AMD, and we even like folks that are coming to us saying, hey, we'll give you money to accelerate the R&D of this non-dilutively if you maybe give us exclusivity in return, and we'll commit to buying like the first 3 years of your entire stock. We're wary about getting put in any exclusivity agreements. We want the best offer we can, so we're shopping it around, of course, but we are at a point already where, given what we've been able to do with the semiconductor tech, people want to accelerate it and people want to buy it as well. And certain companies that we're already currently working with, like Worth, for example, that has thousands of SKUs and has Worth Electronics, which does play into the semiconductor side a bit, is likely a customer that we can reapproach to have some of those conversations as well. But there will be a little bit of overlap in instances like that where we do have some customers that are buying both the industrial and electronic versions. But you know, in the meantime, we have interest in both and have generated a lot of interest in both too.
Yeah, it's great. I mean, definitely revolutionary. So who's a lead and yeah, how
Sure.
much are you putting in?
No formal lead. So we took advisory of Intel's previous CIO. We did a safe note, and we've just kind of been doing rolling close as funds come in. We've been deploying them, and so
Great.
yeah. We
So
figured,
rolling
you know,
close, how much have you taken in out of the 4 million?
4 million of the 5's been committed. Most of that's coming in. You know, everything's going to be ramped up within the quarter. We know the majority of that. You know, over 1.5 has already been deposited. We've deployed a lot of it. There's a lot of signed safe notes and commitments for the remainder of it. So we have some folks like Arma Ventures, Plug and Play, Cedar Park Facility committed $1 million. In addition to that, sorry, I've got a whiteboard wall I'm looking at here. We have the Perry family that's getting involved. We have a couple angels that are getting re-involved as well. And a couple VCs and our folks that we're in kind of diligence steps with in the meantime too.
How much of the 1. So out of the 4 that will be part of this round,
Correct.
How much of that has been spent?
As we've brought in capital, we've deployed it. So our main goal right now, like I said, is twofold. It's scale and it's accelerating R&D so we can get tech like the semiconductor tech out early. So actually, let me swap back to that slide just so there's something in the background. Accelerating R&D so we can get higher tier grants so we can actually deploy that markets. I think people need it and they need it now. But it's also the production scale right now, because things like Evo and Dyad took us years to do R&D on. They're not traditionally designable. They're not traditionally manufacturable. We don't, and 80% has to be done in-house or highly localized. You don't go from, 9 years of R&D to hundreds and thousands of units a month. You build a line that can do a couple. You pass break even, you linearly scale. That's what we planned for. And so we built a line that can do about 5 units a month. So we're bottlenecked at about 375,000 in revenue per month or per quarter. That's our limitation, is that's just how many units we can produce. We have larger interests, like the large order the 4 large customers I mentioned. The problem is, I don't know when we can fulfill that. We have estimations because we've designed out,
Yeah.
we've brought in folks that built more production lines than I have to design a line that can do well over 100 units a month. We have estimations on how long it'll take to set up, how long it'll take to implement new softwares, training, things like that. Because we haven't done it, we don't want to, take on debt or something that commits us to it. So figure
Great.
do it right once before you do it
Ethan,
3 times over.
Thank you so much. This has been great. Obviously great seeing innovation coming into an old sleepy industry like the semiconductor industry. So that's definitely most welcome. Do we have any other questions? Otherwise, we should let Ethan get back to work.
Really quick one from me. Did you
Sure.
say that all the dollars in on the safes are being matched by Cedar? Does a town have a fund? I'm just curious how that works.
It's a local city jurisdiction. To give you quote verbatim of what they said when they came through, basically we approached them saying, look, if we want to get things like that grant capital I mentioned that the state had, the Texas Semiconductor Innovation Fund, you need local partners. In Austin, Texas, unless you're a billion-dollar company, they just don't have the staff to actually help you there. So Cedar Park is within 15 minutes from Austin. They said, hey, quote, we can do a lot better than just tax incentives. We're sitting on a couple $1 billion of liquid capital, and we're willing to bet early. For example, look at Firehawk, or I think Firehawk Aerospace, the 3D printed rocket fuel. Their mayor works with them literally on his off hours, and they're doing early non-dilutive investments to promote job growth in the region. So they asked us how many jobs do we anticipate to bring in a 5-year period? What are we doing here? What are the salaries of those jobs, et cetera? And they say, we can do you one better than tax incentives. We can just write you a direct grant. So that's their quote verbatim words. But, it's assuming that we bring those jobs to Cedar Park, which we need to move and expand within kind of a year of closing that round. It's a strategic timeline for it. And then the Texas Semiconductor Innovation Fund, that's based on all proceeds that come in. So we're getting letters of support from some larger companies that say, hey, this is beneficial tech to the region. So that's why we're talking to both IBM and Cisco at the moment to help back us on that. But the more letter support you have and the more capital you have in, and the more capital you estimate spending on the project and bringing jobs to the region, the more you actually pull from that grant as well. And so that's why, Opportunity Austin, Tokyo Electron's chairman, a couple other folks supporting us on that grant are very helpful.
Excellent. Thank you very much. We're fans of Firehawk, so.
Yeah, no, absolutely. And they'll be able to tell you then I Cedar Park bet early and, gave them capital in a similar manner. So,
Perfect.
and great guys. So.
Well, thank you, Ethan. I think that's all from our side. I think Tim had to run. So fantastic. We connect as an investment committee every week. So next Tuesday morning will be our opportunity to gather up. So we'll reach out after that if there's anything we neglected to ask. But I think we got a pretty comprehensive overview. So we appreciate your time.
Yeah, thank you. And appreciate everyone else's time too. So thanks for it. And hopefully we can keep talking.
Very nice to meet you. Have a great rest of your day.
Thanks.
Thank you.
Take care.
Y'all too.
Bye-bye.